The FAIR team from Meta has come up with a mixture of transformers, and it's an architecture specifically designed for multimodal foundation models. If you take the transformers, the main drawback is that it's been designed for text modality, but in the multimodal system, we have text, images, and speech, and we need an unified framework. So when we have all three modalities, the training set, first of all, becomes very large. And so the computational resources needed for text-only LLMs is much more higher compared to training just for the text modality. So to address this problem, these guys have introduced a mixture of transformers, which is a sparse multimodal transformer architecture. As part of it, they have introduced global self-attention over the full input sequence, but they have decoupled the non-embedding parameters of the model by modality. And they have compared the results with Chameleon 7 billion, which is another multimodal model, which is autoregressive with text and image generation. And they've also evaluated the proposed architecture in the transfusion setting, where we have the diffusion-based loss along with the autoregressive loss. So if we just have the autoregressive loss, then we have the Chameleon setting, and we have the transfusion setting where we also have the diffusion-based loss coupled with the autoregressive loss. So in this video, let's deep dive into this architecture and figure out how they're going about developing this model, gone about training it and evaluating it. So without further ado, let's just jump in. So in order to motivate for the need for a sparse model like the one that they have proposed, what they have done is they have done principal component analysis of the latent feature space, and they have inspected the output of a dense model such as Chameleon plus speech, and they have inspected the layers 1, 5, 17, and 32. And we can see that there's a clear separation of modality, even though you feed all the modalities together. For example, if we look at the layer 5, we can see that text, image, and speech are represented by 3 different colors, and there's a clear separation in the modality in the way the model interprets the modalities, even though we feed them all together. As they mentioned, clearly the model is processing them differently, so that we need a better architecture which actually deals with different modalities differently. So that's the motivation to come up with this sparse architecture that they have proposed, which is the mixture of transformer architecture. So if we take a typical foundation model that is for multimodal generation, for example, the Chameleon model, we typically feed them the tokens for different modalities interleaved between them. For example, we feed the text token and then mix the image token with them. We again have the text tokens, and all these are fed directly to the foundation model. And we have the autoregressive objective in order to train this model in the pre-training stage. But with the mixture of transformers, what they are proposing is the sparsity in order to reduce the computational cost. More specifically, they're saying they use sparsely activated architecture. So with the mixture of transformers, it's a sparsely activated mixture of transformers architecture. So what does it mean and how do they go about it? So let's take this architecture. We can see that different tokens are coming in for different modalities. We have the text in yellow, the speech in pink, and the images in blue. What we initially do is we have this indexing logic in order to index each of the modalities and then pull them out separately. Once we apply the modality indexing logic, you have all the text separated and grouped separately, and you also have the speech separated and the images separated. Because we have now separated them, we treat them separately and we use a modality specific weights. What it means is that you could see that the query, key, and value for each of the modalities is now separately and they are activated separately. For example, for the speech, we can see that there's a weights for query, the separate weights for key, and separate weights for value. And this is the speech specific weights. So once we apply these separately, we then reorder them, meaning that we go back to the initial order that they came from. For example, once we reorder, we could see that this sequence resembles the sequence in which it came. So once we have the reordering sorted, then we do a global attention mechanism. We do a global attention with this one, and we get the output of the global attention. And with the same modality indexing logic, we once again apply the modality indexing logic, and we separate the text, speech, and image. And for the layer normalization and also for the feed-forward network, we have separate weights for text, speech, and image. And so we again apply those separately for each of the modalities, and again comes the reordering buffer. Then we get the actual order in which the input arrived, and of course we have the output weights which process them to give the output that we need. And we can apply both autoregressive objective, or we can apply a diffusion objective, as we will see next.
So with that information on the architecture, if we look at the algorithm, it might be much more clearer. So we can see that we are iterating through the three modalities, which is text, image, and speech. And for each modality, we are getting the index of each of the tokens, and then we are grouping the tokens by the modality. So we have grouped the modalities, we have indexed the modalities, and now we apply modality specific projections. For example, this is the weights for query for the modality, let's say text, and this is the key and this is the value, and we have specific weights for each of the modalities. And once we have done this modality specific thing, then we go for the global self-attention, which is the standard self-attention, but in this case we are restoring the original sequence of the input, and we are doing the global self-attention. Once we have done the global self-attention, we once again iterate through the modality, and we do modality specific output projection, modality specific layer normalization, and modality specific feed forward network, and finally layer normalization. So this resembles a typical transformer before the output is produced, but we are doing it modality specific. Similarly, at the input, we are doing it modality specific in order to reduce the computation. After doing all of these steps, obviously we get the output from the transformer. In terms of the experiments, they do 3 multimodal experimental settings. With each setting, there's increased complexity both in training objective and training modalities. Now let's look at each of them and see how they go about. So the first one is chameleon setting, where they do autoregressive objective for both text and images. So this is the diagram for autoregressive objective. So we have the text sequence, and we also get the images as a sequence using the variational autoencoder tokens. And for each of the output token that we get, we try to predict the next token, and we match it with the actual next token. And that's how we train with the autoregressive loss. And that's the chameleon setting. And in terms of the model hyperparameters, they start with models as small as 37 million parameters and scale all the way up to 7 billion parameters. And for the mixture of experts, for the comparison, they use expert choice, which is a state-of-the-art routing method that's used in the mixture of experts. So the main idea of mixture of transformers is to speed up pre-training or improve the pre-training. So what they do is they take the 7 billion parameter model and find out how well it converges compared to a dense model. So they say that mixture of transformers achieve the dense model's final loss, which is 120 steps. So the dense model seems to achieve its final loss at 120 steps, but the mixture of transformer achieved the same objective in just 60,000 steps. And across the multimodal scales ranging from 37 million all the way up to 7 billion, mixture of transformer consistently delivered significant speed up in image modality across all scales, outperforming the dense model and mixture of expert 4x. So they compare with the dense model, which is chameleon, and they also compare with mixture of expert 4x, and they say that mixture of transformer consistently delivers significant speed up. So let's find out how the speed up looks like. So this is the training steps. So like we said before, 120,000 steps is what it takes for the dense transformer to converge, but the same training loss is achieved with mixture of transformer in just 60,000 steps. They have showed the same with the chameleon 7 billion training loss. They have also shown that the training loss for mixture of transformers is pretty less. When it comes to images, again, mixture of transformers has a pretty less validation loss, indicating that it's definitely the go-to one when it comes to multimodal training. In the next setting, they increase the complexity by introducing speech as the third modality alongside the text and images. So it's pretty much the chameleon with now speech included. And for the training set for the speech, they use Spirit LM, which was introduced in 2024 in this paper, as the speech data set. And they use an in-house tokenizer, which is a variant of the Dino SR model, to extract the speech tokens with a vocabulary size of 500. And they included with the text and image training data set at a sampling ratio of 1:6, and they create a sort of mixed data set of speech, text, and images. And they do the same experiments, and they again follow the same autoregressive objective, but with the speech included. You have the next token prediction going on with the speech as well, similar to the text and the images. And they come up with plots similar to that of the first setting. They compare how the training step progresses compared to the dense, and they show that very less number of steps needed for mixture of transformers to converge. So MoT accelerates pre-training for speech modality, reducing loss faster than dense. And they also say that this is a substantial computational efficiency, and MoT also achieves comparable or lower validation losses. You can see that the validation loss is pretty low as well compared to the dense one or the mixture of expert one. So they say that MoT achieves comparable or lower validation loss than the dense models final loss of images and text tasks. They go on to try out different variants of the model, as in like they start from 443 million parameter model all the way up to 1.5 billion parameter model. And in all the cases, they show that mixture of transformer is far better and compute efficient. Third and last setting is that of transfusion setting, where we have the autoregressive objective for the text, but we have the diffusion objective for the images. So we feed a Gaussian noise to the input, and we go through 1000 diffusion steps in order to arrive at the generated output. And we compute the diffusion loss rather than the autoregressive loss. In terms of the performance, we could see that even in this setting, the MoT model converges very fast compared to that of the dense model or the mixture of expert 4x model. One of the surprising findings is that of the 760 million MoT model outperforms the 1.4 billion dense baseline model. So it's not only the lower parameters, but also the lower computation that comes with the MoT. And it can be witnessed by the three scores for evaluation, which is a CLIP score, FID score, and CIDR score. So with the CLIP score, the highest score is better, and we can see that MoT 706 million parameter model outperforms the dense one. Similarly for the FID score, where the lower score is better, it's just 21.145 compared to 24.688 for the dense model. And when it comes to CIDR score, a higher score is better, and we can see that the MoT model gets a higher score of 0.32 compared to a score of 0.286 for the dense model. That's pretty much about the three settings that they are evaluating their models for. So with that performance gain with MoT, they show some empirical analysis. Empirical analysis is done on the AWS with the P4DE24X large instances equipped with A100 NVIDIA GPUs. So the first one that they do is horizontal scaling, where they examine MoT scaling trend by varying the GPU count during training. So the question is, if we increase the GPU count, how does the performance improve? That's what they are showing in this plot. As they increase the GPUs from 16 to 32 all the way up to 256, they say that MoT benefits with the increasing number of GPUs, as in the percentage steps required for MoT to match the image validation loss of a dense model decreases from 42% to 21% as we increase the GPUs from 16 to 256. Similarly, there is also a decrease from 75% to 50% when it comes to text validation loss. And this clearly suggests that scaling pre-trained compute resources further enhances the efficiency of the performance gain. And the next one that they go for is the wall clock time, where we are aiming to achieve the best model quality with a given fixed GPU time, basically. So you fix the GPU, you fix the time, and then now you want to find out what's the best model that we can get within this given time. That's a primary objective with the wall clock time. As we can see from figure 19, which is this one, we can see that for a fixed amount of GPU training time, MoT significantly outperforms both the dense transformer baseline and mixture of expert 4x. So that's clearly witnessed by this red curve, which is way below the dense model or that of the mixture of expert model. Similarly here, the time to match dense model is way lower compared to that of the mixture of experts or the dense model. The same applies for training loss. Time to match that is significantly lower with the mixture of transformer, indicating that it is super efficient when it comes to training in lower time frame. That's pretty much it. Basically, they then go for related work and they finally conclude just saying that, just mixture of transformer is a sparse and scalable architecture designed to address computational challenges of a multimodal model pre-training. So I hope that is useful to you guys. So that pretty much wraps up the paper on mixture of transformers. I will see you in my next video. Until then, take care.